In this video, we're going to look at how to use the standard molar enthalpies of formation in order to calculate what we call the standard molar enthalpy of a chemical reaction. This new measurement represents the delta H of a chemical reaction, assuming that all of the reactants and products of that chemical reaction exist within their standard states of matter, and assuming that the reaction takes place at standard atmospheric temperature and pressure. The formula for the standard molar enthalpy of reaction is actually fairly intuitive if you remember the formula for how to calculate delta H in general. So to calculate the standard molar enthalpy of reaction, we're going to take the sum of the standard molar enthalpy of formation of all of our product molecules, and from that we're going to subtract the sum of the standard molar enthalpy of formation of all of our reactant molecules. As mentioned before, this looks very similar to the formula for delta H, where we take the potential energy of all of our products and subtract the potential energy of all of our reactants. So if you remember one formula, this formula here becomes fairly intuitive. Now, one of the problems that a lot of students make is mixing up the mechanism for Hess's law and standard molar enthalpy of reaction calculations and kind of combining the two. What we'll see in this first example here is that using one and using the other will yield the same result overall. So first, we can do a little bit of a review about how Hess's law would work. Remember that standard molar enthalpy of formation reactions and their delta H values always correspond to the synthesis reaction here. So this assumes that methane gas, carbon dioxide, and water all exist as the AB component in a synthesis reaction, and therefore these standard molar enthalpy of formation values here all correspond to the synthesis reaction. That means if we want to calculate the standard molar enthalpy of formation with methane, assuming that methane is a reactant rather than a product, we need to take the synthesis reaction of methane, which is elemental carbon plus hydrogen gas, and flip it around so that it's the decomposition reaction to show that methane is a reactant rather than a product. So this means our standard molar enthalpy of formation value, the delta HF value, needs to be multiplied by -1 to show that this was flipped around from the original synthesis reaction. However, we can use the carbon dioxide and water values directly here because there is no modification that needs to take place, at least in terms of direction. So if we write the enthalpy of formation reaction for carbon dioxide, we see that we're reacting one atom of elemental carbon with one molecule of oxygen gas, which means that we can use our standard molar enthalpy of formation value directly like this. We need one small modification to the enthalpy of formation of water, however, because again, in order to balance this chemical reaction, we need two molecules of hydrogen gas, which means that we're going to make two water molecules like this, which means that we need to take our standard molar enthalpy of formation for water and multiply it by 2. That means that when you add all of these numbers together with the modifications using Hess's law, if you do this correctly, you should end up with the delta H value of -802.3 kilojoules per mole. So again, this is nothing new. This is simply using Hess's law in order to calculate the standard molar enthalpy of reaction value using the standard molar enthalpy of formations of each of the reactants and products. Now what we're going to do is the same calculation, only using our general formula the standard molar enthalpy of reactions formula. The good news about using this is that we don't need to modify the direction of any of our enthalpy of formation values. We can use these exactly as they are, and all we need to do is refer to the number of each product and reactant in our overall equation. So we have one carbon dioxide here, which means that our total standard molar enthalpy of formation of our products is going to be negative 393.5. Again, this is the enthalpy of formation value of carbon dioxide. And to that, we're going to add our enthalpy of formation of water, negative 241.8. But because we have two water molecules, we're going to multiply this number by 2. And when we add these two numbers together, you should get negative 877.1 kilojoules per mole. And again, this represents the total standard molar enthalpy of our products. And from that, we subtract the total standard molar enthalpy of our reactants, which in this case is methane, which has a standard molar enthalpy of formation of negative 74.8 kilojoules per mole. And because there's only one, we don't need to modify this number. Now, the next step here, when we're solving for our standard molar enthalpy of reaction, is to correct the sign. When we subtract a negative number, that's effectively adding a positive number to this negative number. So we can say plus 74.8. And then if you do this calculation here, the number that you should get is once again negative 802.3 kilojoules per mole. So what we see is that using Hess's law traditionally, where we write out the synthesis reactions and then modify them and then put those modifications on delta H like this, gives us exactly the same calculation as we would do using the formula for standard molar enthalpy of a chemical reaction. And we don't even need to bother with canceling everything out, because that's just the way that this formula works. Now that you've seen how Hess's law and the standard molar enthalpy of chemical reactions formula give you the same result, in part 2 of this video, we'll look at a more in-depth example about how we can use this formula in practical situations.